Okay, so today we're going to talk about Chapter 5, Section 8, Polynomials in the Real World. We're going to fit data to linear, quadratic, cubic, and quartic models. Our essential understanding is that we're going to use polynomial functions to model many real-world situations. The behavior of the graphs of polynomial functions of different degrees can suggest what type of polynomial will best fit a particular set of data. We can use a graphing calculator to help us find functions that model data. So if we have this table here, here's our x values. They increase by 5, and our y values are 10.1, 2.8, 8.1, 16, and 17.8. We can either use any of these 3 different regressions, linear regression, quadratic regression, or cubic regression. So when you plot the data points, and you guys can do this, you can plot or graph in Desmos. So let me type that for you. So we graph in Desmos, and you can set up a table. But you have to, if you don't have a graphing calculator, you have to find a linear regression calculator. So find or quadratic reg or cubic reg online. And that's what I search when I pull up a search. I just search linreg online calculator, quadreg online calculator. So let's go through and see what we'll be encountering when we solve these problems. Okay, so this is the n+1 point principle. For any set of n+1 points in the coordinate plane that pass the vertical line test, there's a unique polynomial of degree at most n that fits the points perfectly. So the principle confirms that any 2 points determine a unique line. 3 points that are not on a line determine a unique parabola. 4 points that are not on a line or parabola determine a unique cubic, and so forth. So check this out. 2 points is a line. 3 points is a parabola. So 2 points, you think about a line, which is x, and then 2 points is, so power of 1, we need 2 points. Power of 2, we need 3 points. Power of 3, we need 4 points. So that's the n+1 point principle. All right, so let's look at using a polynomial function to model data. What polynomial function has a graph that passes through the 4 points, -2, 1, 0, 5, 2, 9, and 3, 36? So if we use the n+1 point principle, we have 4 points. So that would mean this is a cubic because it's 4 points, 3, power 3. So the generic form of the cubic is y equals ax cubed plus bx squared plus cx plus d. And we need to substitute the x and y values of the 4 points to get 4 linear equations in 4 unknowns. So essentially, let me grab okay, so we're going to take y equals ax cubed plus bx squared plus cx plus d, and we're going to make 4 of these equations. One with -2, 1, one with 0, 5, one with 2, 9, and one with 3, 36. So where there's, let's do the negative 2, 1. So everywhere there's a y, I'm going to put a 1. Everywhere there's an x, I'm going to put a negative 2. Everywhere there's a or a b or a c or a d, I'm going to leave as it is. So negative 2 squared plus c times negative 2 plus d. And we're going to go ahead and negative 2 times negative 2 times negative 2 is negative 8. Negative 2 times negative 2 is 4. And minus 2c plus d. So now I'm going to do that. So I did it for 2, 1. Now I'm going to do it for 0, 5. So anywhere there is a y, I'm going to put 5, and everywhere there's an x, I'm going to put a 0. When I do this, thankfully, I get, all these are zeros. Anything times 0 is 0, and I get d is equal to 5. Yay! So actually, let me highlight my 4. So 2 down, 2 to go. Do the same thing with 2, 9. So everywhere there is a 9. A y, it's a 9. Everywhere there's an x, it's 2. Squared plus c times 2 plus d. And then we simplify that. Two times 2 times 2 is 8. 2 times 2 is 4. 2c plus d. That is as simple as it's going to get. Okay, we're still on step 1. One more. 336. So everywhere there's a y, I'm going to get 36. Everywhere there's an x, I'm going to put a 3. Plus d. And so we get 36 equals 3 times 3 is 9. 9 times 3 is 27. 3 squared is 9. 3c plus d. Boom. Okay. Get 4 linear equations and 4 unknowns. Check. So step 1, check. Write the system in augmented matrix form. Use the RREF, or reduced row echelon form, function to find the coefficients a, b, c, and d. All right, so we are going to, let me show you how to input those. Okay, so I went to my dougbabcock.com, and I'm going to have 4 rows, and then I'm going to have 1, 2, 3, 4, 5 columns. So 4 rows, 5 columns, submit. And then I'm going to input. I am going to input my A's first, B's second, C's third, D's fourth, and then my numbers last. So this would be negative 8, 4, negative 2, 1, and it equals 1. My second one gives me 0 for A, 0 for B, 0 for C, 1 for D, and it equals 5. My third one, I have 8 for A. So my A's are going in the first column. The coefficients of mine. 4 for B, 2 for C, 1 for D, and that equals 9. Last but not least, I got 27 for A, 9 for B, 3 for C, 1 for D, and that equals 36. All right, so when we do reduced row echelon form, we get A is 1.6, B is 0, C is negative 4.67, and D is 5. So once again, A is 1.7, B is 0, C is negative 4.7, and D is 5. Use cubic regression. So our equation is 1.7x cubed plus 0 x squared is 0 plus c, all right, so that would be a minus, minus 4.7x plus 5. And then we're going to use cubic regression with the 4 given points and check the solution. So I'm going to go ahead and go to Desmos and graph. So let me show you how to put plot the points instead of just regular graph. So I'm going to put these 4 points in, negative 2, 1, 0, 5, 2, 9, and 3, 36. So if you look how closely the equation that we found, all of our points land on that point. So the solution checks. Check. All my points are on the equation of my line. Okay, so we're going to do the same thing with the milk. So milk production in 1955 was 16.5, in 1980 was 22.4, and in 2005 was 22.9. The chart shows the dairy farms. So what linear model best fits the data? We have 3 data points, so that means we have a linear model. So we're going to use the model to estimate milk production in 2000. So what we do is we input the year, and then we input the milk production. So 55, we had 16.5, 80, we had 22.4, and check this out, this 105, that is 2005. So think about if 0 is 1900, then 2005 would be 105. So we go to our linear regression calculator. Previously, we just had data points and no other pertinent information. Here we have these data points, but they tell us what linear model best fits this data. So we know we're going to linear regression. We get, when we plug this into a linear regression calculator, we get A is 0.128, B is 10.36. So if I'm using this, I'm going y equals 0.128x plus 10.36. We want to look at our r. The closer r is to 1 or negative 1, the better our data fits. But you can see this little guy here is a little bit off the line, so he's not going to fit so awesome. But we're going to use it to estimate milk production in 2000. So So we're going to plug in 100, because if our starting point is 1900, the year 2000 is 100 years from then. And then that's just a simple calculator check, and I have probably the most basic calculator there is in the world. 0.128 times 100 is 12.8 plus 10.36 is 23.16. So y equals 23.16 billions of pounds. All right, so here is one more way we're going to use the point principle. The graph shows a quadratic model for the milk production in problem 2. The quadratic model fits the data points exactly because of the n+1 point principle. Given that both models are good fits, so this one is saying this isn't a linear model. This is a quadratic model. So for a linear model, the model continuously rises. For a quadratic model, it has down, down, end behavior. So it starts down and ends down. It shows slowing growth, a turning point, and then a decline, eventually to 0 and negative values. So our r-squared value of 1 for the quadratic model, the linear model is more likely to represent milk production since it shows a continuing increase. People are drinking more and more milk. Deciding whether a model is reliable is important to consider the source of the data. Data generated by the law of physics or a geometric formula will have a mathematical model that fits the data and yields accurate prediction. With other data, such as sales records, you can approximate the data only within or close to the domain over which it was generated. So you have to stay close to your data points. If you get something way out here, it's not going to give you as accurate information. Using a model to predict the y value outside the domain of a data set is extrapolation. Estimating within the domain is interpolation. Interpolation usually yields reliable estimates. Extrapolation becomes less reliable as you move on, and that is the highlighted information. So make sure you write down this paragraph right here.